Hello all, welcome back. In the previous video we did implicit differentiation. Next topic in this is parametric differentiation. But before that, let us understand what do you mean by parametric equations. There is a picture in front of you. It shows a ride, and as you can see here, this is your position. This is your seat where you are seated, right? So as the speed of this rod increases, this is your main, I can say this is the main stem, and this stem is rotating like this, and there are subsequent branches that are attached to this stem, right? And you are attached to the second branch, means branch of a main branch, right? So is there any way to represent your position mathematically? Of course, x and y coordinates or the Cartesian coordinates, they can represent your position at any amount of time. But that representation, that mathematical equation of your path, or you can say mathematically the locus of your position, this is going to be a complex curve, right? So the analysis of that curve becomes very difficult. So can there be any other way to represent or to analyze your position mathematically? The answer is yes. So parametric equations, parametric, you can say coordinates, they help in analyzing complex curves more easily, right? So let us represent your position by assigning one parameter, right? What do you mean by a parameter? That I will tell you afterwards. So if your position, let us say this is the origin, right? This point, I'm writing this as O, okay? So let us say like this, okay? This is O, your initial position, and then this point is, I'm writing this point as A, okay? So there is a branch from O to A, so I can draw this with a straight line O to A, okay? This point is A, right? And from this point A, your position is, I'm writing your coordinate as, or the point of your position as point P, okay? This point, I'm writing this as P, and like this, okay? Now as your ride rotates, there is a relation between the amount of rotation between this branch OA and AP. And what is this condition? Let us assume that if this branch OA is rotating with an angle theta, if the amount of rotation is theta for this, then the amount of rotation with respect to this rod OA is twice, right? Means AP will rotate twice the angle that this OA will rotate, right? So if OA is rotating with an angle theta, after some time, then angle of rotation of AP with respect to OA is 2 theta. This is a given relation. For example, I'm taking this, okay? So total amount of rotation for this AP with respect to horizontal line, that is going to be 3 theta, right? So let us represent this mathematically, not mathematically, diagrammatically. How I can represent this? That let us say this is your OA, right? And after some time, it has rotated by an angle theta like this, okay? This angle is theta, right? This point is A after some time, okay? This is your origin. So amount of rotation of this branch AP is twice the amount of rotation of this OA. So with respect to OA, angle is 2 theta, right? So let us draw this. So this is your amount of rotation, right? And if I extend this line like this, so if this is theta, I'm saying that this is 2 theta, means with respect to OA line, your amount of rotation is 2 theta, right? So with respect to horizontal, your total rotation is 3 theta, right? So your position now is this P. With respect to horizontal, total amount of rotation is 3 theta, right? And I can represent now your position with respect to a single variable, which is theta. How we can do this? Let us see. Okay, so this whole phenomena is written like this, that this is your OA, your initial branch from the hinge or from the initial joint of the stem, OA, and from A to P, this is your P is your position, right? This angle is 3 theta, as I told you earlier. This is theta, right? So if I have to find out your x and y coordinate, so using simple trigonometric equations, not the equation but simple trigonometric ratios, I can define your x and y coordinate in terms of theta, right? How I can do this is that x coordinate means the distance from this O to point A, right? So this distance is 4 cos theta in this triangle OA and this point. In this triangle, you can see that your vertical height is 4 sin theta, and I can write this horizontal distance as 4 cos theta. Okay, and similarly from point A to point P, this horizontal distance is 2 cos 3 theta, because angle here in this triangle is 3 theta, right? So I can easily write down x coordinate in terms of theta as from O to A, horizontal distance is 4 cos theta, and horizontal distance from A to P is 2 cos 3 theta. Okay, this distance is 2 cos 3 theta, and this distance is 4 cos theta. So 4 cos theta plus 2 cos 3 theta is your x coordinate of point P. Similarly, y coordinate you can define as 4 sin theta plus twice sine 3 theta. Okay. Now what is the use? It looks like that it has become more complex, but that is not the case. Why it has become more, or why it is looking like more complex? Because initially there was just a single coordinate x and y. But remember, that was just a representation of certain position. This is again a representation of a position, right? No matter you are writing two different terms with a plus sign, right? It is looking like a complex equation because you have two terms, and that too with cos theta and 3 theta. But once you know the angle theta, this will be only a single value, right? 4 cos theta will give you one value, and 2 cos 3 theta will again give you a value, right? A constant. Okay, so why it has become more easier? Because point is, what is a use of this using parametric equations is that initially the point P, using Cartesian coordinates, you need two coordinates x and y, and then using some more conditions you can define the locus of the point or the path of your position, right? In Cartesian system it will involve two variables x and y, but here both x can be written in terms of theta and y also can be written in terms of theta. That means two variables have been reduced to a single variable, which is theta. Okay, so this theta is called the parameter. This is your parameter, and using this parameter you have changed the x and y coordinate into a single parameter, which is theta. Of course, the combination of this theta with some trigonometric ratios will be different, right? But the variable has been reduced from 2 to 1. Okay, that's why it is called a parametric equation. And the next topic which we are going to study today is parametric differentiation, because once we know the curve, then of course there will be some point of maxima, there will be some point of minima, or practically in this very example you may be asked that what is the point, or where the point will lie where you will feel more sensation. Okay, where you will feel more sensation, either it will have a maxima or it will have a minima, or where the gradient is maximum. Okay, so all these analysis of a curve will only happen if you represent the equation of a curve more easier. Okay, so parametric equations, or you can say the parametric coordinates, they are very much an important part of mathematics. Okay, so having said this, that what are parametric equations, let us come to the topic parametric differentiation. Okay, so next topic is parametric differentiation. As you know that initial coordinate is of course x and y, so basically what you have to find out that dy by dx, value of dy by dx, how the y coordinate is changing with respect to x. But here we have that y is a function of t and x is again a function of t. Okay, where I am calling t as a parameter, right? In the previous example, theta was parameter. You can take any variable, it doesn't matter, right? So y will be differentiated with respect to t, and again x will be differentiated with respect to t. So how you will obtain the value of dy by dx? It is very easy, right? Because you can write dy by dx as dy over dt, because y is a function of t, as I said earlier, and this is upon dx by dt. So you separately find out the derivative of y and x coordinate with respect to t, and then divide both these values, right? So you will get the value of dy by dx, right? So again, I am repeating, how to find out dy by dx is you differentiate y with respect to t, you differentiate x with respect to t, and then divide both the values. You will find out the value of dy by dx. Okay, that's all for parametric differentiation, and in the next video we will do some more examples on this parametric differentiation. Okay, thank you.